All right, yeah, I think just recording these sessions would be pretty cool. We could
Yeah.
just put them on because we are two out of three of us here are YouTubers. So it's a good idea to start recording these things because we love ourselves and we're practically narcissist people, and we just want to document whatever shitty thing it is that we do. All right. Problem 4P1. Okay, I'll go first, and then Vlad can go second, and then Ziad can go third. Is that good?
All right, sir.
All right, cool. All right, get parity. First thing that came up to my mind was just like this brute force, which is pretty much just right shifting and then ending it with one. And that's it, and then just like flipping the parity bit. And that was it. And then this blew my mind. This was really cool. So num ended with num -1 pretty much gives you, I think. Oh, it just clears the least significant bit, right? Is that it?
Yes.
Yeah, that's what it does.
The
Yeah.
least significant set bit. Yeah.
Yeah, least significant set bit. So this makes it a little bit faster. And then in this one, I came up with this, doesn't work. It's a shitty solution. I don't know why anyone would come up with a shitty solution when solutions as clean as this exist. But the there are a couple ideas that I'm using here that I think would be pretty cool to kind of like think about. I am using a lookup table, and my lookup table, the first index is the length of the kind of bit set that bit set that I'm looking up, and then the index into it is basically the bit set, like all the different combinations, and then the value is the parity of that. So we start with this like starter lookup table. By the way, this code doesn't like pass all the tests right now, but the idea, I think I can like still try and like explain it. But I basically have this table, and then what I do is that I create a mask. So for example, when I have this table to begin with, I double the longest length that I have, so which is 1 here. So I double that, so that's 2. And then I take 2 bits of the input string, and then I basically divide and conquer it. So I basically use whatever I have in my lookup table. So right now, a string of length 2 would be like 1, 0, for example. I divide that in 2, and then I look up the parity of 1 up from here and look up the parity of 0 from here. And then after I have the parity of these two, I can basically calculate the parity of both of them, because that's basically just, like if the parity of both of them is 1, it becomes 0. If either of them is 1, it's pretty much like XOR.
Yeah.
And then, actually, XOR wouldn't work, would it? I think it's AND it. Or,
Wait,
because
what are
if
you
it's
saying?
0, parity of 0 and 0 should be 0, right?
Yes.
Parity of 0 and 1 should be 1, 1 and 0 should be
Yeah.
1, and then 1 and 1 should be 0.
Yeah, it's like sorry.
Is that XOR? Yeah, that is XOR. Never mind, I'm dumb.
Yeah.
All right, cool. So yeah, pretty much I look that up, and then after I look up, for example, 1 and 0, now I know that I just calculated the parity for 1, 0, right? So I create a new entry, and that new entry will have 2, because the length of that is 2, and then inside I will have the string 1, 0 as key, and then the parity, which is 1.
So wait, can I go over an example of your thing just to make sure I get it? Because I feel like with the example. So imagine the number was like a 4-bit number, and the number was 1010.
Yeah. So let's go over
Right?
it here.
So this is what I was understanding. So yeah, if you set the number to just 1010.
1010. So first I take a look at my lookup table. So this is how my algorithm works. Look at lookup table and pick the longest kind of key that I have, right? So longest key right now is 1, key length.
Yeah.
And then I'll double that. That gives me 2, right?
Yeah.
And then I'll scan the bit set that length. So basically right now it becomes like 1, 0, right?
Yeah.
Because the rightmost 2 bits. So basically what I do is that I basically left shift 1 by 2 and then minus 1, and this gives me a mask of 1 1, right?
Yeah.
And then I AND it with the input number.
Yes.
That I have, right? And then after I scan the bit set, I get 1 0, right?
Yeah.
But then the longest length that I can look up here is 1, right? So I basically have to divide this into two parts. So one part is 1, one part is 0, right? And then I call the same function with 1 and 0, right?
Yes.
And then so basically what I do at the top part of this function, I basically take a look at the biggest length. And then if I call this function with this number's length, if the length of the number is bigger than biggest length, then I just basically create that mask and call this function again. If it's not, then I will go and basically divide it in half, and then I get the first parity and the second parity, right? And over here, I basically take a look at the lookup table. If the lookup table exists, then I just return from it. I think I should do that at some point here. I don't know what is going on in this. Oh, here. I take a look at the number in the lookup table. If it exists, then I will return it. Otherwise, I will divide it in half and then I call the same function. And after I've calculated that, I basically take XOR the parity of this first parity and second parity, and then I enter that into my lookup table because it doesn't exist because it didn't quit when it was here, right? And then so basically this is what happens. In this example, we have 1 0, and then that basically what happens is that it comes down here, right? Number 1 0 doesn't exist in the lookup table, so it goes down here, and then it finds the first half and the second half by calling this function again, and it'll go down the same path again, and it will return because now individual bits of 1 and 0 do exist in my lookup table. And then I will XOR these two, which gives me 1. So 1 XORed with 0 gives me 1.
Yeah.
And then I will enter my lookup table this. My lookup table basically becomes, like, the new entry in my lookup table has a length 2. And then the only thing that I've calculated was 1 0, right? And this one will be 1.
Yep.
And then, so basically, if you have a long piece of input string that is very kind of repetitive, then this algorithm does really well because it basically builds the results as it looks it up. So basically, it's kind of like an example of dynamic programming.
Yeah.
But it also is divide and conquer because it basically divides it in half and then calls the same function again on it. So the idea is nice. Implementation is really messy, and it's hard to get it to like the idea was like it's probably like if we have similar problems, we could potentially use this idea for other problems. But is this a good solution for this problem? Not really. I don't think so. These are much nicer in my opinion.
Right. Okay. So it's like I like the idea though. You were trying to go for pretty much LUT implementation, but with some sort of like you were trying to improve, I guess, like an existing LUT implementation, like from EOPI.
Yeah.
So, I mean, it seems like definitely a good place to start though. I kind of like the idea.
Yeah, so that when I saw the lookup table, like I didn't really fully read the solutions because I wanted to see if I can like get the hints from the first couple lines of the solution when I was reading it. And this is like the bullshit that I came up with because I was like, oh, lookup table, this is probably what I can do. But actually in the actual book, they have this lookup table solution where they just keep a giant array of like 16, all possible 16-bit values, and they look it up, which is pretty cool. I actually didn't mind that.
Yeah, I guess the thing that we discussed the first time we looked at this together, Arshan, was that basically your thing works as long as there's a lot of repetitive ones, and when it's beautiful when your lookup table.
Yeah,
like
because
if you're
it's
not
memory
doing
efficient too.
More as long as your lookup table is smaller than the one that they made. But if you were to use this like millions and millions of times, it would eventually probably go through all possible variations of values, and your lookup table would have like take up as much memory as there is possible integers.
Yeah,
which is like basically insane.
Yeah, it's like in the order of exabytes.
So that was the conclusion, I guess, for your job. But I really like this one. I actually was thinking about like looking at it and trying to do it myself, like without looking at your solution and seeing what you did differently or what.
Yeah, so like
might do that again.
if I conveyed the idea correctly, we can probably try and finish this solution, because I think not for this problem, but for other problems, we are probably going to take an approach like this, because this is really kind of like gives me like dynamic programming vibes.
Yeah, this is a beauty. I'm a big fan. So I think I'm gonna try this soon and try it myself, and then look at yours after and see what was different if mine works.
All right, sick. I like that. We can maybe bring that up in our next episode of Arshan, Vlad, and Ziad tried solving problems. All right, cool. So Vlad, you go ahead.
Yeah, do you want me to share my screen?
Yeah, actually.
You cannot start screen share while the other.
It.
I've never used this. I've never used Zoom, man. I'm very excited.
Oh, so the way you do it, I think there's a share screen button down there.
Oh yes, I'm figuring it out. I can pick the screen?
Yeah, you can pick the specific application or your entire desktop. Ooh, look at this. Beautiful.
Can you see that?
Yeah.
Okay, so yeah, literally, since I already went through most of these solutions once before, I kind of had like a rough idea of what all of them were. So I mean, I basically have all the stuff that they had. But this last one here, the XOR one, was like pretty interesting. Because it's literally divide and conquer. It just keeps splitting it in half.
Yeah.
The only thing is that they like hard code the size of the max int to 64 here, right?
Yeah.
So it assumes the max is 64 bits. So you could like.
I think we can probably change this to include like any length.
Yeah, because you can just literally just like, what's it called? Recursively keep calling the same thing.
Exactly, and Python doesn't really like have any limits, so you can use like infinitely big numbers. It'll all handle it under the hood, which is pretty cool.
Yeah,
I had no idea.
Yeah, this is a pretty well-known solution. It's like for, I guess, for interviews when you really want to. I guess it's one solution to throw in there, to kind of give at least the understanding that you understand that this is something viable. That avoids any sort of recursion or anything else. If granted that here the caveat is you have to know the number of bits using the number bookend. So
yeah, that's pretty cool though.
But yeah, the most amazing thing was this, or was it this beautiful thing? This was like actually magnificent, especially in the variance of the problem, because like just like this like right here, the x minus 1 part, like the fact that subtracting 1 actually just like removes the least significant bit that's set and sets everything else to 1 is like incredibly useful after this.
Yeah, that's some juicy trick. I really like that. And also they show up in the variations too.
Yep.
Yes. But yeah, Ziad, do you have any other things that you noticed from this? Because I don't know. If you want, we can just go to the variance.
Yeah, it's a pretty simple problem. I don't think.
Yeah.
No, because I kind of like went over this trick during the variance problem. I don't think there's anything that I like want to add to this. Like the only thing is it's a really cool trick, right? It's one of those things that if you know, like it's really going to help you in a lot of problems because the pattern repeats in these scenarios, and it's very useful. It's a very useful trick to know. So
yeah, sick.
But yeah, so here, so what are the variants again? Oh yes, the right
propagating the rightmost bit. So if you have like in the example that you just showed there. So if your number basically ends in a 1 and a whole bunch of zeros, you just want to flip all of those zeros.
Yes. So you just want to flip all that and or with the original number. So this num minus 1. So here this. So that is the same, like, I guess you can see up here, I actually just gave an example. So, like, when you have this as your x, when you do the num minus 1, you can see that the last 4 bits got set to 1.
Mm-hmm.
And then since the bit, like the leftmost bit, which was this one right here, gets changed to 0 when you OR. Oh, wait. Oh yeah, you just said all the ones. Yeah, this all makes sense.
Yeah.
Never mind. Yeah, this is very simple. Sorry. Yeah, I don't think there's anything to
Yeah,
show about
basically
this.
all what happens is that the rightmost bit turns into 0, and all the zeros to the right of it turn to
Yeah.
1. And after you OR them, all the bits to the left of the rightmost bit remain the same. It's only
Yes.
the rightmost bit that changed to 0, but it's going to get ORed with a 1 because it's the same number.
Yeah.
And then all of the zeros to the right of it will get ORed with 1s.
Yes.
That's pretty much all it does. Yeah, my solution is exact same.
Mm-hmm. Yeah. And then for the mod power 2, so the beauty I realized of this is that, so when you have some, like, in binary, something that's to the power of 2, like 64 in their example,
Mm-hmm.
if you want to mod something by 64, then all that happens is you want to basically remove all the bits starting at that bit, like the 64th bit,
Mm-hmm.
and every... Oh, yeah, so you want to remove that and all the more significant bits, because, those are all powers of 64, or like multiples of 64. So basically you just want all the bits after the power of 2 bit. So like these bits here. So once again, you can just, like when you do that x minus 1 trick, it's beautiful because now if you just AND, you get all these remaining bits. And this number that you just got, the x minus 1 number, has zeros everywhere else. So everything before that, like all the bits that are more significant and equal to this power of 2 number are all set to 0, which is beautiful.
Yeah. So, Ziad, did you take a look at the variations as well?
Yeah, I did.
Oh, okay. So you know what this problem is.
Yeah, I know. And I came up, so some of these solutions are, especially the second one, it's exactly the same. I got the exact same. And then the first and third problem, I used a ternary operator instead of like an if statement here, but the logic's pretty spot on, so I agree with that.
Nice. Wait, does Python have ternary operator, or did you do the if
Yeah,
else
it's
clause?
in Python, like you can do it, but it's a lot nicer. It's instead of like the usual like colon and everything, like with the 2 different results that you can have, it's just return something
if condition else some other thing.
Yeah, you could have done, what is it, return?
So it's like return num,
Yeah.
Right. Copy paste that.
Wait, Vlad, are you using Vim?
Brother, of course.
Hey, I like that.
And then otherwise
else 0.
It would have been like that, right?
I guess it's nice because it's not like it fits into one line, but really there's not much difference.
Yeah, I realized that. Like the book has some like very, very compact notation for solutions sometimes.
Oh, really?
Kind of like,
there are some Pythonic ways of expressing things that are really interesting, and also if you're not familiar with Python, really
especially some of the like the list unpacking stuff or whatever.
Exactly.
I was like looking at some of those, like holy moly!
That's some weird shit.
Yeah,
that was really interesting.
Something or X and whatever, right? Yeah.
But yeah, the one-line if statements are like very, very nice most of the time. But you have to include the else.
Yeah. Otherwise, you'll get. I mean, you can do else none if you don't really have anything to return. But yeah.
And then the last one is power 2. So basically, it's only a power of 2 if it has 1 bit set.
Mm-hmm.
So the logic was exactly the same as this one here, except now you just check if that final result is equal to 0 or not.
Yeah.
Because if it's equal to 0, then that means there was no other bit set. And then you just not that, I guess.
Yeah.
Nice. Yeah, I think this one was pretty simple. I think we should just move on to 5.1 because.
Sure. Yeah. I mean.
Yeah. But this x minus, like basically every time you want to do anything with bits after some bit that's set, this is like so amazing.
Yeah.
Absolutely. Yeah.
It's a gorgeous solution. All right. Wait, 5.1. Yeah. Okay.
The Dutch flag shenaniganry.
Oh yeah, that was a good.
What was this one? Oh yeah, the 2 pass. So I think, so you guys both did this, right?
Yeah.
Like
Wait,
this
wait.
problem.
Let's go over the problem again. I kind of forgot a little bit what was in the problem.
Yeah. So the problem is, you can go ahead, Ziad, this time.
I think, if I remember correctly, so it's been a while, but something like, so you have a list of numbers, and these numbers, it's an unpartitioned list. So let's say you have 0, 0, 2, 1, 2, 2, 2, right? And then the idea is that just like, it comes straight out of the concept of the Dutch flag, which has 3 colors. And you want to partition this list into 3 or like more depending on the variation of the problem, distinct classes where you have, based on your pivot that you originally set, either less than, equal to your pivot, or greater than.
Oh, okay. Now I remember all of it. Okay, cool.
Yeah, so there's just like 3 different groups that is defined by the pivot, I guess.
Yeah.
Yeah, so this one was actually pretty amazing, especially when you look at the variance again. I was like very impressed with all this logic. I'm really interested to see what you guys did with the variance, because it was.
I did not do the variance.
Okay. I was so amazed by the solutions that I got to them, or like I found like this general proof, I guess, or general theory that you could use, but we'll see. So yeah, the start, like the obvious one was just to put all the elements less than the pivot to the left of the pivot.
Yeah.
Kind of like quicksort, and then like do the same thing, do all the ones greater than the pivot, and then you're left with all the elements equal to the pivot between those two. So do 2 passes through the list.
Oh, interesting. So this is basically 2 passes, one from left to right, one from right to left.
Yes.
You swap them, so you're changing stuff in place too. So you're not really like using extra.
So there's no extra memory, and it's still linear, but it's 2 passes.
Yeah.
And then I realized, or they said that you can do in 1 pass, and I was like, oh my goodness. And then this became so beautiful, because I didn't like realize the magic of this, but I don't. You guys, I guess, have read the solution too, but
no, I haven't. So yeah, go for it.
So the logic is like this. So you have like so you use 3 pointers. So basically you have a running set of 3 lists as well within the same list, or 3 like groups. So you have the group that's less than the pivot, you have the group that's equal to the pivot, and you have the group that's larger than the pivot. You're gonna say the groups that are less than the pivot are gonna be the very leftmost part of your list. The ones that are larger than the pivot are gonna be the very right, and you're gonna start building up those lists from left to right. And you're going to keep the ones equal to the pivot right beside the leftmost list. And then you're going to basically like adjust that list as you get as you look at the elements. So the idea is this. Basically, you have one pointer that's pointing at the leftmost list at the element that is unseen or that should be switched. So every element left of that left pointer is already good, or less than the pivot.
Oh, okay.
Right, so that the pointer is pointing basically at an element that should be swapped if an element less than the pivot is found.
Yeah.
Then you have a pointer at the very right, or the rightmost pointer, which is pointing at an element that is 1 index left of the right list, which is the list that's greater than the pivot.
Yeah. And
then finally, you have a pivot, or so you have a pointer pointing at the last. Actually, let's see this one. The leftmost unknown. Yeah. So then you have one that's pointing at the 1 index right of the list of all the values equal to the pivot. So if you were to, for instance, like here, let me show you. If you were to look at a list, this is kind of like. So imagine your pivot is like 5. So imagine you have like these numbers. Oh God. You have these numbers, and then you have 5. And then you have 5 again, and then you have some more numbers. And then, okay, here maybe let's imagine we have some unknowns. And then here you have like numbers greater than the pivot. So right now, the leftmost pointer would be set to right here, because everything to the left of that pointer is already good. It's less than the pivot. So here, pivot equals 5. So this is leftmost pointer right here.
Yeah.
Then there's a rightmost pointer, or right pointer, which is pointing to, it would be right here, because everything to the right of that
is good.
Is greater than the pivot, so you're good there. And then last of all, you have another pointer basically pointing at the unknown.
Mm-hmm.
So the unknown in this case could have been, like it's the one that's kind of iterating through the list, and the unknown would be one right of the values equal to the pivot. So it'd be like at the 1 here.
Yeah.
Assuming that it's already looked at the 5 here. So now comes the interesting thing that the book does, which is like what happens if as you're moving these pointers. So the way you step through this algorithm is you initiate left pointer all the way to left, you initiate right pointer all the way to the right.
Yeah.
And you say your unknown
is
pointer is also equal to left one.
Yeah.
You keep iterating unknown, and every time you find a value that matches one of the 3 categories, you basically try to put it into that group.
Yeah.
So if you were to start here, you would be like, okay, unknown pointer, okay, it's less than pivot, so let's swap with pivot. Or leftmost pointer, so let's swap leftmost pointer and increment both of them. So leftmost pointer and pivot, or the unknown pointer, are here. So you do the same thing. Oh, it's less than the pivot. You increment both of them. You get here, it's still less than. You get to here. So this is when it gets interesting. So here, your unknown pointer now looks at the value and it's equal to the pivot.
Yeah.
So since it's equal to the pivot, it doesn't put it into group 1, or it doesn't put it into the less than group or the greater than group.
Yeah.
What it does is it just increments. Right?
Oh, okay.
So then what happens again? It sees a 5 again, which is equal to the pivot. So once again, it just increments, because that means that the group, that like you're fine. That it's this group is this equal to pivot group is already in its right place, which is exactly one.
So
right
wait, does it increment the unknown pointer now?
Yeah. So the unknown pointer is always increments.
Yeah.
But neither of the other pointers increment if the value is equal to the pivot.
Okay. So now we get to 1. So what happens there?
Now we get to 1. So you're like, okay, so ideally I'd want to put this 1 into this leftmost list.
Exactly.
Right? But like you're like, shit, there's a 5 there, which is the previous one. But then you realize if you just swap the 2, it's beautiful.
Oh, fuck!
Because then you put in the 5 here, you put in the 1 here.
Holy shit, that was so cool!
And so now...
questions, reactions.
So now the beauty...
Now
you're good.
Now you're good, and you increment both the pointers. So now the leftmost pointer is pointing once again at an element that is not part of the list. The unknown pointer is incremented, and then this. So the greater than list. So let's just, for interest's sake, let's make this a 6 here. So now you get here, and you're like, okay, this value is greater than the pivot value, right?
Yeah.
So you have to put it into the rightmost list.
Yeah.
And that's the pointer here. So the pointer, so what would happen is you'd put it into here. So you'd put the 6 into here, and you'd put the 7 here, because you swap the 7 with the 6. That's because you have no idea what number was here before.
Yeah.
You just know that the pointer is pointing at an element that is unknown and that is not part of the list.
Exactly.
So now your unknown pointer is still here, because it's still unknown. You have not incremented it.
Yeah.
Once again, you look at this value, and you're like, okay, it's greater than the pivot. So now I need to put it into this spot, which your rightmost pointer already decremented into. So you put it here, and then you put the swap here, and then you're like, okay, oh shit, it's like greater than the pivot again. So once again, I would swap it here and put the 5 here, and then lastly, you would look here, and you'd be like, okay, this one's equal to the pivot, and then you'd step here, and now you see that your unknown pointer is equivalent to your rightmost list, and your list is sorted. So this would be the partition. And you do only one step through.
Yeah. That was really cool. But, I mean, in terms of complexity, it's not much better than the 2-pass.
So it's exactly the same. They're both linear, but technically it's 2 times faster because it does 1 pass versus 2 passes. But that doesn't really matter, because we always talk about, like, in, I guess, like, an exponential size, or like... the powers.
Just 1 second, sorry.
In big O notation, right?
Right. We would drop the coefficient.
Yeah, so it doesn't matter. So it's like O to the 2n, big O of 2n versus big O(n), which is still big O(n).
Yeah.
Exactly.
But there's a little bit more, like, processing happening in this one, though, than the other one.
Yeah. There's a few more checks.
A few more checks.
And so that's exactly what happens here. I mean, basically, while your unknown index is less than that high index, or your rightmost index, then what you're doing is you're checking, is it less than the pivot? If it's less than the pivot, then you swap unknown and the lower index, and you make sure to increment low and unknown. Otherwise, if they're equal, remember, you just increment unknown, because if they're equal, then you can just skip, like you can move on to the next element. And then if it's greater than, you swap with the rightmost side and you decrement just the rightmost. But notice it's very important that you decrement just the rightmost index, and you are not decrementing this one right here.
Yeah.
Like you would.
Because after you check higher, you have to just stay there and check again if it's still
Yeah, you
higher.
have to keep swapping it. Yeah.
Yeah. Okay.
Because
Cool.
it's unlike. So then yeah. So this is like the final solution, I guess, the final beauty. But the most amazing thing is then you wonder, like, because this kind of goes into the variance, but what you wonder is, like, what if you had like 4 different partitions or 5?
Sorry,
or
guys.
6? Could you?
Sorry to cut you off. We have less than a minute. I'm gonna have to give you guys another Zoom call.
Because we're on the free tier, eh?
Yeah, we're on the free tier.
Okay.
Broke
Yep.
gang. But yeah, let's actually end the call, and I'm gonna make a new meeting, and then we can continue.
Okay.
All right, just one sec. Don't remind me again. Later, new meeting. Ooh, hi. Stop video. Invite. Copy URL. There we go. Join with computer audio. All right. Ziad, you're in, right? Okay, cool.
Yeah.
Let's wait for Vlad to come in. There we go. Hello. Okay, Vlad, share your screen again and continue.
Yeah. Okay, so this is when it gets like really, really exciting, because then you can like generalize. Oh, what the hell is going on? You can generalize because you realize that all that's happening is now what happened is you have one pointer pointing to some group you described.
Yeah.
That group. So you have like, let me just. Okay, so you have some groups. So you have like group 1, which is technically equal, or is less than 5, which is your pivot. Then you have group 2 in this case, which is equal to 5, which is your pivot, and group 3, which is greater than 5.
Yeah.
And you can basically use this method to define any group you'd like, or any categories of any 3 groups you'd like. In this case, we just chose to make it exactly with a pivot in these 3 groups. And so what you realize is you can actually use the same technique if you made this with 4 groups. So if you had like another group 4, which is equal to maybe specifically 6s, and then you'd have a right pointer. So here you have 3. You had 3 pointers, one that was like leftmost and then rightmost, and you had an unknown one. But that unknown one was just technically right of the leftmost one.
Yeah.
So like, so if you looked at the pointers, what was really interesting is so I'll just do like this. So you had like left pointer, and then you had right pointer.
Yeah.
And then the other one was technically right of the left pointer. And now, so if you want to do with 4 things, you technically have one that's left of the right pointer, and you'd use the exact same logic. So you'd have like 4 trailing pointers, and you could do the exact same logic and build up the list exactly the same way, but like with 2 pointers from each side. And then you could do the same thing with like 5 groups, and you could basically make this like infinitely many groups as you want, with infinitely many pointers as you want, that are just all like trailing each other from left to right, kind of.
Gotcha. Okay.
Which is like amazing. So you can one pass partition a list into
any kind of groups.
Yeah, which is like super amazing.
Wow, that was.
When I saw this on the book, I was so shocked. It's so good.
Yeah, it was so beautiful.
Yeah.
Wow.
Yeah. So, like, for example, with the because there's one of the variants is if you're given an array A, which is it's variant 2. You're given an array A of n objects.
Yeah.
With keys that take one of 4 values. So there's 4 different groups, technically 4 values. You have to reorder the array so that all objects that have the same key appear together. So that was so for that question, you can do like exactly this logic that I said. You basically do this exact same thing, but now you have a 4th pointer here, or a 4th index, but that tracks the one that's left of the rightmost one, and has the exact same logic as this unknown one here.
Isn't that the variance 3? I think that's variance 3 of this same problem.
Variant 3 is the Boolean valued keys, right?
No, I think that's the variant 4.
The variant 4 is Boolean as well, but you have to keep order.
Oh, you have to keep order. Okay, yeah. Now I remember.
Yeah. Did you do all the variants?
Yeah.
So how did you do them? That's what I was... Because I had... So what I did for variant 1 is I did exactly the same solution as this one.
Yeah.
Like exactly the same thing. Because there's 3 groups and everything. The only question is you have to define the groups, right?
Yeah.
You have to somehow have a pivot.
Yeah. Do you want me to show my solution for variant 1?
Yeah, let's see.
Yeah, sure. Yeah,
Okay.
sure. Let me just quickly show you like.
Yeah, you show me yours.
So mine was exactly like the same one as before, but the only difference is now it's apparently I was impressed this worked. But so, all you do is you have to just define the pivot to be the mid value of the 3 values. So I just wrote a function that finds the middle value of the 3 because there's 3 distinct values in the array, and then you do the exact same thing.
Oh, okay. So I think it'd be cool if I showed my solution. Yeah.
Yes. So let me stop sharing
because
and show yours.
Because
I literally.
okay.
Yeah.
Okay, let me start sharing my screen real quick. Okay, cool. So for variant, so this was problem 5P1 var1. Okay, cool. So what they said with regards to the answer is that it doesn't matter how you partition them. So like you can partition them basically like 1, 3, 2, or 1, 2, 3 if the 3 values they have are like 1, 2, 3, right? So what I have here is that I just like because I saw this one line in the book where it basically just in the solutions it just had this one line, but it would not really use it.
Yeah, I saw that too.
Yeah.
I didn't use it.
So I basically did this. I set red, white, blue. So I just defined 3 different variables, and I just equal them to 3 none, like a 3 tuple of none values, right? But what happens is that as I go, so basically this is a 2-pass version.
Yeah.
Right. So I basically go through it once, and then I go back. Right. But what happens is that the first value that I see, regardless of the value, I just set my red value to be that. So for k in range len 1, so this is basically going from left to right, the first value that I see, if it's not red, then if the red is not defined, then I set red to be that value.
Yes, and then you're skipping that if statement every time after that. Yeah,
every time after that, this if statement gets skipped, and if anything is red, I don't care about its value if it's like white or blue. If it is red, then I basically just swap it. And when I come back from the other side, if blue is not defined, the first value that I see from the right side is going to be blue.
Yeah.
Right? And then if I reach red, then I break, because it means that by that point I have exhausted, meaning that all of the reds by that point is to the left. And if I'm going from right to left and I reach a red, then I know that I can break. So after that point, whatever value that I see is blue, I just swap it with the right. So whatever's remaining in the middle is whatever that is not red or blue. So it should be white.
Yeah. So you basically did the 2-pass solution.
Yeah.
Essentially.
Yeah.
Yeah, that's you did exactly that, and then you just defined red to be that first value that you see, and then blue to be the other. Oh wait, what did you do with blue? You did blue is equal to Oh yeah. So it's equal to
the first value that I see. Yeah. So the value that I'm seeing
and it won't be red in the case that there is 3 different values, which there has to be in this case. So it's fine.
Yeah. So after this passes through entirely, red's gonna be to the left, blue's gonna be to the right, and whatever's in the middle is not checked. So it could be white or it could be not.
Yeah, that's a pretty nice solution actually, because mine does a 2-pass too, but I do 1 pass to find all 3 values and get the mid value, like the mid number or whatever, and then I just partition, because I assume there were numbers.
Yeah, well, this is also numbers, because we're running them against the same tests, but yeah.
Yeah. But so yours doesn't matter at all. Yeah, the number. But yeah, so I just did 1 pass to find the middle value of the 3 numbers, and then I did exactly the same 1 pass solution. So mine still ended up being a 2-pass, but I feel like yours is cleaner because you don't have to do that like messy helper function, which I made very inefficiently for sure, to find the middle value.
Wait, let's take a look at your solution here.
Yours is like yours the 2-pass thing actually works out really beautifully when you don't know what the pivot is.
Exactly. You know, it's just it's not about the pivot anymore. It's just about the condition that puts it in that group. So if it passes that condition, then it is good.
Yeah.
I
So-
like that better. Nick.
But yeah, so which is why I thought that if you saw my solution, it would kind of, because like you said, it checks are kind of messy. But
yeah, you can even see using Dutch flag partition, the second function. I think the first one was actually something else I did that I don't even remember what I did.
No, this is it. Pivot, find mid val, and then use the last problem solution.
Yes,
That's cool.
It's I literally just need to find the pivot.
Yeah, you just.
Yeah, the one up there, I did something magical. I remember now. I don't remember because I was so impressed that this worked. And you can see I only did one modification, which I set the end value. Only modification required was to set the end value since we don't know what it is at the start. Oh, yeah, I did a similar thing to you, but with one pass. You can see there that I set the end val. I don't have an end val set at the beginning.
Oh, so yeah, basically you have a start val and then you have an end val, but you don't have it set.
Yes.
So you basically.
I do exactly what you did. I set the start val to the first element in the list.
Yeah.
I then don't set the end val, and I set the end val to the first other number I see. That's not equal to start val.
Oh, okay, yeah, that way you can do it.
And then I one pass it. I do one pass only.
Yeah, okay, that's pretty cool too, actually.
Yeah, I didn't even think of that. Well, I didn't realize I thought of this.
Interesting. The 2-pass version kind of looks cleaner a little bit, but maybe if we can just like clean this up, I think it might be just as good. But this was really cool. So you basically take a look at the first value that you see, that's the start val. Second value to see is the end val, which is the same case with my solution too, but you do it in one pass.
I do it in one pass. And
That's
I think
cool.
I just named my variables really long. Very verbose.
No, that's good. That's good. I mean,
very hard. So it looks very messy, but I think it's not that long actually.
No, this is good. I would rather look at code that is written like this rather than my own code. But here, there's just the exception that these are just algorithm questions, so you can.
Yes, but this was the beauty. Yeah, I remember now. It was the beauty that you can set the start val, find the first value that's not equal to start val, and set it to end val right away.
Mm-hmm. Yeah, pretty much.
And then do the exact same solution because you then know the other value is just the one that's not the one of the three.
Exactly.
What was variant 2?
Variant 2 was the same thing, but 4 flags.
What did you do with 4? Did you just run 3 times? Loop 3 times? Oh, yeah.
Let's see what I did. I think I just put red in the beginning, so I just did one pass, so all the reds are to the left. And I did another pass that was green, right? And then I did another pass, but like when I did the green pass, right, I would know where the greens would end, right, from the right side.
Yes.
So I basically did from like, and I also know where the reds end.
Yes.
Right. So I just have the same problem, but with like 2 different categories, white and blue.
But now in your third pass, you still use the same range, which was the entire list.
In my third pass, I do from range I, and I the last time I set it to the right.
That makes sense.
So I go from left to right, but I basically, whenever I see green, I break. So it's not really length of A. I'm just lazy. Over here, I could have recorded the value of like wherever the green ends.
Yeah.
But here, I just said if I see green, I can break.
Yeah. I see what you mean.
Yeah, so it's basically 1 pass left to right, 2 pass right to left, and then third pass in the middle.
Yeah. So what's really interesting so the passes are actually not like full out passes because technically what you do is the first pass is a full list pass, right?
Yeah, and second pass is also a full list pass.
It's not because it will automatic.
Oh yeah, you're right. It stops wherever you read. Yeah.
Yeah, it breaks after the first list was already sorted, so it's going to be equal to. It's going to break, so it's going to be less by the number of whatever red is. Yeah. And then the third pass is technically is equal to the total minus the number of greens and reds.
Exactly.
And for the 2-pass solution, like originally, it's actually not 2 full passes. It's 1 pass plus like 1 pass minus how much there was of that first group.
Yeah, I think we can go off here and like generalize it. But let me actually just like type some stuff out here. I think if the number of groups that you have are, let's say you have like n groups, and in group number 1 you have A number of items, B number of items, C number of items, and D number of items, right? So this is probably like what we're doing. So in first pass, you do A plus B plus C plus D. And then in the second pass, you do B plus C plus D. And then the third
Yes.
pass, in this case, because I'm going from left to right, I
Yeah.
do basically b plus c.
Yeah, exactly.
And then after I do this, this is basically like all the passes. So if
Yeah.
we add all of these, it's basically a plus 3b's plus 3c's plus 2d. I was hoping this would turn into something nicer, but it's not really.
A nice like binomial series.
Yeah, I was hoping it would like turn into something where I could basically like, because a plus b plus c plus d is the size of input, right?
Okay.
So I want it to be like O of, you know, like the number of variables groups that I have times n or something like that. But wait, if a, b, c, and d are all equal, so let's say there's the same number of items in each group.
Yeah,
right?
On average, that would be true.
Then in this case, this would become 1 plus 3 plus 3 plus 2, which is 9.
Yeah.
Right? Which is 9/4 of n. So this would be O of 9/4 of n.
Beautiful.
All right. I'm done with this head assery.
Yeah, but if you look at mine, so I think mine was just the one pass version all over again.
Oh, okay.
Fourth pointer.
Vlad. I like how we like find something and then we just stick to it throughout all the variations.
Yeah, so oh my goodness. Yeah, mine was I wrote a lot of comments can you go up? What was the first? I wrote like a nice story at the top or something. Amazing how this Dutch flag partition method works for partitioning a list of n distinct groups, not just limited to. Oh, you know what? I also realized that my what's it called? My the thing that limits the line length is set to 120 for some reason.
So yeah, you can change that in PyCharm.
Yes, I'm gonna change that. I just noticed right now. Because I was looking at yours and I was like, what the hell? And now I checked mine and I was like, oh.
Yeah, I changed mine to 80, I think.
Yeah,
and that was
80's
because I was
common.
working with a project and that project required that. But yeah, whatever.
But yeah, you can see, yeah, so it doesn't have, yeah, whatever. It was exactly what I explained in the comment up top. But, yeah, so this time I used the 4 pointers and I did a similar thing this time. I had a start val, an end val, and another val that was called the before end val, the third pointer.
Yeah.
And now I set them all that like as I go through the list, and then there's a bunch of swapping that happens and stuff.
Yeah,
but it's a one pass.
It's a one pass, but it's it's kind of
it's a bit of a mess.
It's a bit of a mess.
Like it's very beautiful because you can generalize it to as many groups as you want in one pass.
Exactly. That's really cool. I'm very, very happy with this.
Then there's. Yeah, let's just finish up the last two variants and then.
So in this one, oh yeah, I just our tests were basically true or false. So this was pretty much easy. It was basically like a one pass because if not, then I just swap and that's it.
Yep.
And then problem 4, what I did the same thing, but I just went from last to beginning.
Yeah, exactly.
And that preserved.
I realized too. It's beautiful.
Yeah, it's really cool.
It's so interesting. Yeah, and then I also what was actually interesting was writing the test for that one, because I was like, how the hell do you keep the?
Oh yeah, I really like that. I really let's pull up, give Vlad due credit for
I was so pleased with that.
Test problem 5. Yeah, because when I saw your test cases, I was like, damn, Vlad, you smart motherfucker. That was really good. I was really.
This one. I think it was variant 4.
Oh yeah,
test was beautiful.
Test problem 5 P1 var 4. This is it. So good. I love this. When I saw this range, I was like, ooh, this guy knows what he's doing. That was really good.
I realized the beauty. I think that this is what they even left. My idea was that the reason why they said to keep the relative order of only the trues was because you can define true to be any values.
Yeah, pretty much.
Any numerical number.
Yeah.
So it was beautiful because then you can just keep track of your by like literally ordering your list in the order of that they appear in.
Yeah. So made it super convenient. Made it super convenient to write this.
Because otherwise checking order was so difficult. Like if they ask you to keep relative order of falses and trues, you would have had to define like a tuple that was the first index would be like the truth or false value, and then the other one would have to be like its index value. You'd have to like double check that.
Yeah.
Or something like that. But yeah, this was very exciting.
Beautiful. Okay, so problem 5.1. Oh, by the way, let's show everything on my screen because I'm recording this. So it'll have the highest kind of like what's it called? frame rate.
Yeah.
Okay, cool. All right. So next problem is 5. Oh wait, Ziad, do you have anything to add?
No, nothing to add, but good stuff, guys. I really like Vlad's here. I didn't know you could do this, so.
Yeah, no,
Very exciting.
this is really cool. So Ziad, definitely try and play around with the system that we set up here, so that you can basically go through our tests.
If we're moving to 5P6, I can take that on if you guys want, because I already, as I said, I have my own branch, so.
Yeah. You should just.
Nah, we just do everything like push to master. It's okay.
I'll merge the branch into master now, but I do have the solution.
Yeah, you can just share it for now. I guess for this time, just share it on your screen, and then from now on we'll do it for Martians.
Yeah.
After this call.
All right, cool. Do you want to share your screen?
Yeah, let me do that. Let me figure that out.
All right.
Oh, this bad boy. I remember this one.
Can you guys see my screen?
Yes, sir.
Yeah, so for 5P6, I believe the question was just you're given a list of stock prices.
Yeah.
So for one stock, you'll be given an array, and this array will reflect the price of the stock over a span of days or time periods. And you want to find the most profit that you'll make if you buy and sell the stock.
Yeah.
So for this, I had two solutions. One of them was obviously a naive brute force approach, and the other one was a better solution. So the main catch in this problem is recognizing right away that, just like in real life, you wouldn't be able to sell a stock before you buy that stock.
Mm-hmm.
So while you may see the biggest quote-unquote profit for a stock on a day, it doesn't mean that doesn't mean that stock you'll be able to sell it for that price, right? Because you have to have it bought it first.
Yeah, exactly.
Right.
Yeah.
So going over the naive solution, this solution has a runtime of O of n squared and space of 1 since we are not allocating any extra memory.
Yeah.
And see, as you can see here, where the O of n squared solution is because we're iterating twice. So the first iteration loop here is where we're iterating over the prices array. Mm-hmm. And then for each element in there, we are checking that we were comparing it with the next element in the prices list. And
it's basically I think this is fairly easy to understand.
We're just keeping track of a running largest profit so far, and we return it after that time. So that's the naive solution. The better solution is to reduce the problem to a single pass, which makes the runtime O of n and space remains at O of 1. So it's definitely a better solution. So here it's pretty simple. Again, the idea is that you this time you keep track of the minimum stock price so far, as well as the max profit that you could make so far, and then you have a single loop. And it's important here to realize that you are going to encounter only one of two situations. Either the stock price that you're looking at currently is the lowest that you've encountered so far, and in which case you're just going to update your minimum stock price, or it's not, and in that case you want to find the profit that you would get if you were selling the stock on the current day. Yeah. So that's how you perform and then you just update the max profit so far to the maximum. The difference and the max profit so far.
Yeah.
And then you
actually, I think in a more Pythonic way of doing this, you could just change this if-else statement to two lines. One is min stock price so far is min of min stock price so far in prices, and then max stock profit so far is max of that.
Yeah, I realized that this problem was actually beautiful because you realize that every time you're doing some comparison, if something is less than, and then you're just setting it to that value, if it is true, then you can just do a max or min comparison.
Yeah, exactly.
Right.
So every time there's a comparison operation, if there's like another function that does that same thing for you, you don't have to do that if or else statement anymore.
Yeah, you can just do min equals min, max equals max.
Yeah. It's so beautiful.
Yeah.
I wrote two if statements, Yeah, I wrote the exact same thing. I did the exact same thing, kind of. Yeah.
If you want to share your screen, just let me know.
No, I don't need to.
All right, so exactly, I think I've looked at my own solution and Vlad's solution and your solution now, and they all look the same. There's only I only have one thing to add to here, and that's basically like a different way of doing this problem. It's an entirely different kind of approach, and that's like it's a 2-pointer approach. I just want to share that with you guys too.
Yeah, let me. Do you want to? I'll stop sharing.
Yeah,
So,
okay, I'll share it now. But wait, desktop. All right, there we go. So for problem 5p6. All right, so this is the brute force one, easy peasy, O(n) squared. This is the one. So I didn't come up with this. I'd seen it on lead code, and up until that point, this was the kind of simplest solution that I had ever seen. But after I saw Vlad's solution, at first I didn't believe it. I thought it was too simple to be true, and then I tried to like write some test cases that would make it fail so that I could go to Vlad and be like, hey, your solution failed. And then I looked at the book and I saw that the book had the same solution. I was like, fuck, he's right. Anyways, but yeah, this one is interesting. I think it would be, I think you guys would appreciate this. Let's go through it. So basically, by the way, first thing that I saw, like first trick that I kind of came up with that I thought it was cool. Every time that you have a list and you want to like pick the values in the middle of the list, so you want to like create 2 pointers that are basically pointing to the middle of the list. This is how I did it. So I right shift the length by 2, so that basically takes the floor of divided by 2, right? And then I do len.
Right shifted by 1.
What? Sorry, I right shifted by 1.
Yes.
Which is
the floor of 1. Yes. It takes the floor. Yeah, because you lose the least significant
exactly.
bit, the one that's 1 or 0. Yeah, this is beautiful.
Yeah.
So that's you divide by 2 and then floor. Yeah, beautiful.
Yeah, so I is gonna be the floor and J is gonna be the ceiling because I just do len A minus this.
Oh, this is beautiful.
Right? Yeah, I was pretty proud.
Anyway, this is a beauty. This is a beautiful thing just to keep in my mind for this.
Yeah. So
right, instead of fiddling with, did I take this? I take the floor to take the ceiling of the middle to get the middle and all this stuff, and it's just no. There you go.
I know, right? Thank you guys. Thank you. You guys are gassing me up. I love it. All right. But this solution, the way it works is I basically take 2 pointers that are in the middle. Let's see. Oh wait, can you guys hear me? I just got a whole lot of notifications. My default microphone changed.
I can hear you.
Yeah.
Okay, cool.
I totally see what you did here. So you're like you're having these pointers kind of go separate ways. So you were kind of like cutting the iteration.
Exactly. Exactly. So that's how I do it. Sorry, just 1 second. Let me remove these if p greater than 30. That's when I was debugging the code. But basically, this is what happens. I take the difference between the two. J is the pointer to the right, and then I is the pointer to the left. So I basically continue this until I has reached the beginning of the list and J has reached the end of the list. Right? This is basically those 2 conditions.
Yes.
And if I is bigger than 0, meaning that I hasn't is not the beginning, I take the difference. If the difference is bigger than the difference that so this P is the price. So it's basically like if it's bigger than the price that I've calculated so far, then I advance I, right? So what I do is that I look ahead basically here. So if like at this point I do, I basically check for. I move I to the left, then I check if I calculated that price, it would be bigger than big.
Greater than 0.
Yeah, I'm kind of looking ahead here. And then after I do that, I know that if I advance I to this direction, then that would yield me a better result. So I basically update my price, right? But then I continue. And I do the same thing. If J, I advance it and see that it yields a slightly better price, then I calculate the difference. Right?
Yes.
And then...
But, wait, does that always have to be true? Couldn't you be stuck in a thing where it would never yield a better difference, but only if you skip over the next elements it would?
So the thing is, if it doesn't yield a better price, then I just advance them.
Beautiful.
Yeah.
But even if it does yield a better price, you still advance them again after?
No, because I hit continue.
Continue.
I continue.
Oh, okay.
Yeah.
Wait, but why don't you? Oh, never mind. You can't because you don't want to advance the other one. You want to advance one at a time.
Yeah, you want to advance one at a time.
Ah, and then if they both fail, you might as well advance both of them.
Yeah, exactly. So when do they both fail? That means that your gradient is giving you 0. That means that you're already at a local maximum, right? So imagine like a sine wave, right? And you're basically starting from the middle of the sine wave and you're moving in both directions until you hit the, for example, plus pi over 2 and negative pi over 2, right? At that point, if you advance I, meaning that if you take I to a little bit to the left, it's going to yield you a worse price. If you advance J, it's going to give you a worse price too, right? So what do? You just force this to continue so that you can basically cover the entire list.
Yes, you just skip that local peak or local drop.
Yeah, local maxima.
Yeah.
Yeah. So this was the main problem that I like. Usually when I was trying to come up with a 2-pointer solution for this myself, I would always start from the left and go to the right, and that would always yield something bad because I would find like the first local minimum, and then I would like my algorithm at that point it would yield that as the best result, or it would continue into like a infinite loop. It was really hard to make that algorithm work if I was starting from the left. But if you start from the middle and then move in both directions, that will definitely yield you the best solution.
Yeah, but you can also starting from the left is exactly what the book solution does, right?
Oh no, this meeting will also end in 10 minutes.
Oh yeah, well I think we're I'm gonna have to go in about like 10, so this should be perfect actually.
Yeah, it should be perfect. Sorry, what were you saying? The book starts from left?
I mean, the book does very much. Well, it doesn't do the I guess it doesn't look ahead.
It doesn't look ahead, yeah. And it's not a 2-pointer solution. It just goes and finds the minimum price, and then if the minimum is bigger.
Yeah. There's no point. But, yeah, there's no... Yeah, you're right. Yeah, this would be... Yeah, you'd have like a 2 pointers, but one of them would just be like jump. Would jump to the new best one. But anyway, yeah, I see what you're... This is actually beautiful, though. Because this is like so reusable in the future for like future thinking for me.
Yeah, I think this is a cool thing to kind of keep in mind.
Yes.
It's a totally different approach, but I think in other problems it would come up again.
And because it's just as good as the other one.
Yeah, it's just as good as the other one. It's Oven.
Yeah.
But
it's not the other once. It was like on a leak code problem about like rainwater. It's a 2-pointer approach.
But that one they start from both ends.
Yeah. Oh, actually, that was the problem that I solved. Sorry. So I took that, and I guess this is because in that one they start from both ends and they come to the middle.
Yes.
But here I'm starting from the middle and going to both ends.
Instead of like a contracting window, it's an expanding window.
Yeah, geez, I had no idea. Wait, you guys are right. I saw that problem.
Yes.
Okay, so this is an entirely new solution. You're welcome.
So in this solution, you start from like shit, and then you start looking for better. But in the other one with the water, I don't even remember what the hell do they do. They start at best case, and then they start looking for better.
Yeah, you have to return the 2 values that yield the most water, because you basically have a function, and then between them.
Yeah.
Actually, let's solve that problem too. Someone can create a protocol for it, and then we can solve it, and then in next week's episode we can discuss that.
Yes.
Very quickly.
We should have like minutes for this, but yeah, let's do variant 1.
Okay, yeah, let's do variant 1 and then end this because it's already gone for like more than an hour.
Yeah.
So what did I do? Find longest equal sublist. What was this?
This was the exact same thing, except it wasn't the exact same thing, but like
I think it was about finding the longest subarray that has equal numbers. So if it's like 1, 1, 1, 2, 3, 4, 5, whatever, then it would return 3 because you have 1, 1, 1. I believe that was it.
Yeah. It just tells you the longest subarray, like what length it is, or does it return the longest finds the length of the longest subarray. So it just tells you the length of the longest subarray. So it's like it's basically that same other problem, except now you're just if you were to find those 2 stock prices and then just subtract their indices, it's kind of like the same idea, I guess.
Yeah, let's take a look at the test. Test problem 5p.
Yeah, look at the test.
Just to be clear on this, the smallest possible value that can be returned is 1, because that would be just single element subarray.
Yeah.
Unless there's nothing in there, but
Right.
Unless there's nothing in there. Yeah. So I guess in my solution, what I'm doing is I just do a one pass through, and then I just gather all the stuff in a lookup
Like
table.
using a hash table, eh? Yeah.
Oh, you have a lookup table. This is interesting.
Yeah, if it's in the lookup, if it's not in lookup table, I'll set the count to 0, and then I increment it right after, and then I just do m equals max of m in this. But I think that would fail.
Ooh, why do you have a lookup table? What in the world?
Because okay, actually this solution doesn't pass. Because I can come up with a test case where it wouldn't fail. Because let's say I do 1 and then 2, 2, and then 1. Sorry, 2, 2, and then 2, and then 1, 1. Sorry. Let's do 1 and then 1. Okay. So this should give me probably 2, 2, 2, right? This should give me 3.
Yes.
But my solution will probably give 4. Yeah.
Oh, it should give you 3. It should give you 3. Yeah, but it's gonna give you 4. Yeah,
it's gonna give me 4. So this is gonna fail.
Oh, there you go. Check for continuity.
Yeah, because I'm not accounting for continuity. Yeah, that's the problem.
You should have like a thing of like. Yeah, you just have to have a thing to know. You just need to know the previous one somehow. Basically.
Yeah, basically, I need to see if it changed, and if it changed, I need to like set the count back to 0.
Yeah, just wipe your thing.
Vlad, did you use a lookup table for this? Because I didn't.
No.
So that's why what if I use the? So I have the brute force one. What does the brute force one do?
I don't know.
Oh, the brute force one does the same thing.
It does the exact same thing.
What's the difference between these two?
You have like some weird return.
I calculate everything and then I return the max. Whereas here I have the max value and I calculate it and I return it.
Oh yeah.
So in the end I just loop through them and find the max. Yeah. So these two, both of them are wrong. Anyways, all right, I'm gonna switch to your solution, Vlad.
Yeah, yours could have worked if you just had a thing to check for when it's swapped.
Exactly.
I don't know.
It's okay. There's 4 minutes left, Vlad. Make it quick.
Yes. So the brute force one is you just literally have 2 loops. One loop is the outer one. The inner one is just one index more than the outer one, and then you just look at the value of the outer loop value, and then just loop through the inner one and count how many times you see that same number.
Oh, okay, gotcha.
And then
super
store the max of that.
Yeah.
And then the one pass is exactly the same as the stock one. You have a counter of the not exactly the same, but you have a value which is the previous value, and then you have the current one, and then you have the current longest list, and then you have the So you have a current longest list, which is like currently it's built. You add to it if the previous value is equal to the current value.
Yeah.
And then once they're not equal, which means that the value's changed, obviously, right?
Mm-hmm.
You just check, was your current list that you just built, is it bigger than your longest list?
Yeah.
And if it is, you see, I did the max thing there instead of doing the if statement. Proud of myself. But
Damn.
Then,
so you guys are not using any lookup tables here?
Not at all.
Oh wow,
Wait,
beautiful.
Is there a way to make that if and else easier than having that if and else there? If they're equal, then increment else. No, I guess not. There's no way of using like a max thing.
You could do it like this.
Yeah, just say
like cur longest sublist equals
so you can say plus equals 1 if
but that's the one line thing, but I'm
no, I think it should be like cur longest sublist plus 1 if val equals prev val else 1.
That would work too.
That's like one way of doing it.
Yeah. Okay. But this is it. You just keep a running count of your current longest thing, and then as soon as the value is no longer the previous value, then you just restart your counter.
That's exactly it.
All right, cool. I love both of these solutions because they're space 1 and then they're O of n.
Well, the brute force is O of n squared, but yeah.
Oh yeah, you're right. Sorry. Brute force is O(n) squared. This one passes O(n).
The classic double looper.
Yes, sir. Okay, cool.
Yeah.
We have less
Alright.
than a minute.
Yeah. But anyways, yeah. Next week we can message which questions. But I
Yeah,
think
we'll message them.
There's some real beauties for you guys. I'm very excited for the next week ones.
Nice, sick. Thank you guys so much. This was really cool. I mean, I think these are super useful for us.
Yes, I think each of us explaining is beautiful because it's just like an interview. So if the other people don't understand, then you're really fucking up.
Yeah, no, it's really good. We're forced to explain to each other, and we see so many different kinds of solutions and ways of thinking.
Yeah.
It's really cool. All right, thank you so much. We have less than a minute. I mean, it's in a matter of seconds now. So goodbye, and till the next time.
Next time, yes.
All right, thank you. Bye.